Hi, my name is Jenna Tran, and this is my Lab 4 video report on oscillations in a spring mass system. In this lab, we analyze the motion of a mass attached to a string that both oscillates vertically and swings horizontally, creating a two-dimensional oscillatory motion. The purpose of this lab is to analyze the motion of a two-dimensional spring mass system by combining experimental data with a computational model and comparing predicted motion to observed motion. There are several key physics principles involved in the system. First, Hooke's law describes the spring force. This force acts as a restoring force and is proportional to the displacement of the spring from its relaxed length. It always acts in the opposite direction of the displacement, pulling the mass back toward equilibrium. Second, gravity acts downward on the mass and contributes to the vertical motion of the system. Third, the system follows the conservation of energy principle. Energy is transferred between kinetic energy, gravitational potential energy, and spring potential energy, but the total kinetic remains approximately constant. Finally, the motion is oscillatory, meaning it repeats over time because the motion occurs in both the x and y directions. The oscillations are coupled, meaning the motions influence each other rather than acting independently. In part 1, I used tracker software to extract position data from a video of the oscillating mass. The video was first calibrated using a known reference length to ensure that the position measurements were accurate and properly scaled. Then I tracked the position of the mass frame by frame, recording both the x position and the y position over time. This process produced experimental data that represents how the system behaves in real life. This data is important because it provides a direct basis for comparison with the computational model. In part 2, I created a computational model of the system using Newton's second law. The model includes two main forces acting on the mass, the spring force and the gravitational force. The spring force is calculated using Hooke's law and depends on how much the spring is stretched from its original relaxed length. This force acts along the direction of the spring. The gravitational force acts downward with the magnitude equal to the mass times gravitational acceleration. These forces are combined to determine the net force acting on the mass. Using the net force, this model applies Newton's second law to update the velocity and position of the mass over small time steps. This iterative process allows the simulation to predict the motion of the system over time. The model also calculates the system's energies, including kinetic energy, gravitational potential energy, and spring potential energy, which are used to analyze energy conservation. The slide shows the comparison between the computational model and the experimental motion. The blue curve represents the computational model, the red curve represents the experimental data observed from tracker. The two sets of data show very similar oscillation patterns in both the x and y directions. The peaks and troughs occur at approximately the same times, and the shapes of the curves are very similar. This indicates that the computational model accurately represents the behavior of the real system. Any small differences between the model and the experimental data are likely due to measurement uncertainty and simplifications in the model. This slide addresses whether the energy principle is satisfied in the system. The graph shows that kinetic energy, gravitational potential energy, and spring potential energy all oscillate over time. This indicates that energy is continuously being transferred between these forms as the system moves. For example, when the mass moves upward, gravitational potential energy increases while kinetic energy decreases. Similarly, when the spring is stretched, spring potential energy increases. Most importantly, the total energy remains approximately constant throughout the motion. This confirms that the energy principle is satisfied, meaning that energy is conserved within the system. Small fluctuations in total energy are present, but these are due to numerical approximation in the computational model and minor experimental uncertainties. To determine the oscillation period, I measured the time between consecutive peaks in the position graphs. For the x direction, I identified peaks at approximately 0.35 seconds and 2.1 seconds, giving a period of about 1.75 seconds. For the y direction, I identified peaks at approximately 0.4 seconds and 2.15 seconds, which also gives a period of about 1.75 seconds. These measurements show that the system has a consistent or nearly consistent oscillation period in both directions. This slide compares the oscillation periods from the x and y directions. Both periods are approximately 1.75 seconds, indicating that the system oscillates with the same fundamental frequency in both directions. The periods are approximately equal, although small differences may exist due to rounding and measurement uncertainty. This result is expected because the motion is a coupled system where the horizontal and vertical motions are identified by the same restoring forces. The similarity in periods confirms that this system behaves as a single oscillatory system rather than two independent motions. Of course, there are several sources of error that may affect the results of this experiment. Tracking inaccuracies in tracker can introduce small errors in position measurements or just analyzing everything in general. Calibration uncertainty may also affect the accuracy of the data. Additionally, the computational model uses discrete time steps, which introduces small numerical errors into the simulation. To prove the experiment, a higher frame rate video could be used to provide more precise data and more careful tracking to reduce measurement errors. The computational model could also be improved by using smaller time steps to reduce numerical approximation errors. Overall, the results show that the computational model successfully represents the real motion of the system, demonstrates conservation of energy, and accurately predicts the oscillatory behavior of the mass. This all demonstrates how experimental data and computational modeling can be combined to better understand complex physical systems. Thank you.